Okay, lecture 14, properties of covariant derivative. This is a continuation of the previous derivations, which I call standard derivation. And this here is a particular case of the standard derivation, which we already derived. So, the first one, the linearity in the first argument over addition. You see, dx1 plus x2 at y is dx1y plus dx2y is a linearity, okay? On this case, this is this addition over here. So this property says that covariant derivative is additive in the direction of vector field x. First argument. You see, that's the first argument, that's the second argument. So let's prove. Let x1, x2, y belongs to the chi of m be a vector fields. You see? Recall from the standard derivation, the standard linearity derivation, we obtain dfx1 plus gx2 is f dx1y plus g dx2y. So if you consider f equal g is equal 1, then you obtain this particular case of the standard linearity derivation. You see? Now let's move to the second one. Linearity in the second argument, also over addition. You see, dx y1 plus y2 is dx1 plus dx2. Now, interpretation. This says the covariant derivative is additive in the field, this case being differentiating on the second argument. You see, this is the second argument, y1 plus y2. Let's prove. Let again x, y1, y2 belongs to the chi of m, the vector fields. So this follows from the rule, okay? This is a standard rule, again, which we derived previously. So dx f y1 plus g y2 is f dx1, dx y1 plus g dx y2 plus, do you remember, this is the direction derivative, x f y1 plus x g y2. Now, for g is equal 1, for f is equal g is equal 1, then x applied to 1 will be 0. So, in this case, this particular case, dx y1 plus y2 is just this first two terms over here, because this will be 0. You see, this one and this one will be 0. And then we prove exactly this linearity on the second argument. Now, just a remark, just for you, you see, fx belongs to the vector, is a vector field, x of m, the chi. There's a chi at m. So there's a vector field. That's important here, that's right. Vector field. On the other hand, x acting on f is the function. You see, x is xi partial f respect to xi. That belongs to R. It's different. You see, fx is a vector field. X acting on f is a scalar. Now, this particular case, attention, coordinates are functions. So if I let f is xj, you just substitute f here by xj. You see, x on xj, xi partial derivative xj respect to xi. So this here, okay, is just delta ij. So delta ij on xi is xj, which belongs to the real. You see, just an important remark that we use in the intrinsic geometry.